All right. Hey, everybody. Thank you for coming. So today we're going to be talking about Bitcoin. And we titled it Bitcoin, What, Why, and How. The focus of the talk is going to be on the tech side of Bitcoin. I'm not going to be talking about the finance. I'm not a finance guy. I'm not an economics guy. This is not investment advice. Okay, this is just tech. We can talk about the finance part later. All right, so just needed to get that out to begin with. So what is Bitcoin? So before we talk about what is Bitcoin, let's just talk about some of the background. So in August 2008, the domain bitcoin.org was registered, and no one had heard of anything about it until then. But you can look back in the domain name registries and see when an address is registered. Then in November 2008, on a cryptography email listserv, somebody with the username Satoshi Nakamoto published like a thesis, like a paper describing a peer-to-peer electronic cash system. As you can read, I've been working on a new electronic cash system that's fully peer-to-peer with no trusted third party, and he just put it out there just for people to read. Then he went behind the scenes, he actually wrote up the code, and in January 2009, just like 2 months later, he released the code for Bitcoin and started running it. January 3rd, 2009 was the Genesis block. That was the very first block, and we'll describe what that means. And then in 2010, Satoshi Nakamoto, who nobody knows who that is, it was just a username on a forum, he gave over the repository, he gave over the responsibility or the permissions to the code to Gavin Andresen. And he said, and basically he took a step back, and no one's really heard from him since. And all the code that runs Bitcoin is hosted on GitHub, and it's open source. So just a little bit of information there. So the beginnings, people say that like nobody knows who made it. That's true, but it kind of doesn't make a difference because the code is all open source. Everyone can see it, and technically whoever wants to can contribute to that code as well. There are some people, like Gavin Andresen gave over the rights as well, but there are people who are in charge, but anyone can see it and anyone can technically contribute. All right, so in order to understand Bitcoin, there's 4 basic technologies that we have to understand. So number 1 is hashing. We'll talk about hashing. Number 2 is blockchain, this word that everyone's throwing around. The third one is a decentralized or peer-to-peer network. And the fourth technology is digital signatures. So these are all technologies or concepts that together form Bitcoin. And if we can understand these 4 technologies, or these 4 concepts, then we'll really fundamentally understand exactly how Bitcoin works. All right, so let's start with hash functions. So a hash function sounds complicated, but it's simply a mathematical equation that takes an input and turns it into an output. So you can take any number, you can take a book, you can take a document, anything that you can type up on a computer. You put it through this mathematical function, and it gives you an output, and that's called a hash function. And it's a way of summarizing information. Generally, what the original point was to take a lot of information, like an entire book, and compress it into a very small, into much fewer characters. So I just put on here a very simple demonstration of a hash function. Suppose we have the word, let's go back. We have the word January. All right, so the letter J is the 10th word in the alphabet, so that's 10. The letter A is 1, N is 14, and so on and so forth. So 10 through 25 represents each letter in the alphabet. So a very simple hash function that we can make up is, let's add together all the numbers. So 10 and 0 is 1. 1 is, let's combine, so 10 and 0 is 1. Let's combine all the numbers. 1 is 1. 1 and 4 is putting those two together is 5. 2 and 1 put them together is 3. 1 by itself is 1. 1 and 8 is 9. And 2 and 5 is 7. So we're compressing those numbers down. Now let's compress them down again. 1 and 1 is 2. We see over here it's 2. 5 and 3 is 8. We see over here it's 8. 1 and 9 is 10. And let's take the 1 and 0 and compress that down to 1. And then we have 7, and that leaves us with 7. And if we do that process again, so we have 2 and 8, that's 10. That's 1 and 0. So again, compress that down to 1. and then 1 and 7 is 8, and we're left with 1 and 8. So if we have this hash function that we just made up, and basically takes the word January and it pushes it, compresses it into the numbers 1 and 8. And that's just a very simple hash function. Generally, hash functions are used to represent very large pieces of information. And more recently as in the last 30 years, we've have something called cryptographic hash functions. And so some of the properties of cryptographic hash functions are that when you take this very big piece of information, let's step back. Okay, so if I have a document and I want to send that document to somebody else, and I want that person to know that they got the document exactly how I sent it, and nothing was changed. So if I have a way, so I can either read them, the entire book, the entire document, which may take a very long time, or I can somehow compress that book down into just a few numbers and read them those few numbers, and then send them the entire book, and let them run through the same hash function on their end, and if their hash function results in the same small set of numbers, then they'll know that they got the exact same book as that I originally sent them. Okay? But some things that we have to be very, very careful of when we do that is that if I have two separate books, those two separate books, when we put those two books through a hash function, we have to make sure that the hashes, the outputs, are not the same. Are not the same. They don't collide. So we have to make sure that it's. So a few things that we have to make sure of is that it's relatively easy to calculate the output of any given input. The output will always be the same for any given input. So if we take two books, if we take one book and we put it through the hash function multiple times, every single time we'll get the same exact output. We also have to be sure that it's impossible to predict the outcome of a hashing function. So when I have a book, we have to make sure that it's mathematically unfeasible with our current knowledge of math and our current computers to be able to tell ahead of time what the hash will come out to be. It is very difficult to find two inputs that have the same output. That's what we said. And then any tiny change in the input will drastically change the output. And it has many uses in hashing in computer science. So just as a quick demo, we can even go to any. So one hashing function that's commonly used is called SHA-256. So just to show what this looks like. So this is an online tool, and if I type in any message, if I write "Hello World," we see here that there's this long number, and this long number is the result of these characters put through the hashing function. And notice that if I add even a single character, if I add just one dot, many of the characters in the resulting output will change. So I'll put one dot there. So we see that one tiny change in the input significantly changes the output. Okay? So this way, very often when you download something from the internet, and you'll see that it asks you if you want to download the MD5 check. So that's because with just a small string of characters, with just 20 or 30 characters, you can download the program, run it through the MD5 algorithm on your own computer, and then come out with those few characters and make sure that you got the program that the initial developer intended for you to download. So that would be a use in just cryptographic security to make sure that you have what was intended to be sent. Another use case for this is with something called I believe it was called hash cache. And this was in the late 90s. And when they just started with email, they were having a problem with spam. Too many people were sending it was too easy to send emails. So one of the solutions that somebody proposed was to force people to find a specific hash. Now we said that when you're starting off with an input, it's impossible to to know ahead of time what the resulting hash is going to be. So the only way to find a specific output is to just try it many, many times until you find a hash that you're looking for. So for example, let's open up that website again. Yeah, sure. So people have spent their entire lives building these equations so that there's no way to go back. No, it's
lossy compression.
It's lossy compression. Basically, changing one piece of the input will change in a cipher like the Caesar cipher, right? So we just shift the alphabet. So over there, each one letter represents one output in the ciphertext. Right? So over there, when there's a one-to-one relationship. So if there's 10 letters in the input, there'll be 10 letters in the output. So therefore, there's some sort of relationship between the two. With the more modern ciphers and these hashing algorithms, there isn't a one-to-one relationship. I mean, they're specially engineered so that the output is so significantly detached from the input that there is no way to go back.
No way, or just we don't have the ability.
With hashing, there's no way to go back. You can brute force it. You can brute force it. You can try every single combination, but there's no way to look at the result and work and reverse engineer it.
You mentioned MD5 hashing.
Yeah.
I've always wondered if I can change the program, I can also change the hash value.
So the answer to that, yeah, you're right. But the answer to that is that now you have to change it in two different places. You have to get access to wherever we're downloading the program from and change that, and then you have to get access to the website that's hosting that MD5 check. If you get access to those two, then yeah, but it just makes it that much more difficult. Okay, so we have this hello world. Now, if I told you to find a hash where the entire hash resulted in A's, it's not possible to be able to predict that. Because, like we said, when you give an input, there's no way to tell what the output's going to be. The only way to get a hash that has any sort of properties that is all A's, that starts with two A's, is to try it repeatedly until you find it. So this hash cache system to protect emails from spam basically said we can't predict the entire hash, right? But what we can, because there's no way to do that. There's no way to do that besides brute forcing, and to get a specific hash where every single character is what you want would take longer than the time of the universe. So, but what you can do is try to get just the first character to be something that you want, right? Because each of these characters you can't try that. So if we put an A there, we get an 8. If we put a B there, we get a C. If we put a C there, we get a 7. And you see, so we can try 10 or 20 or 30 different tries, and then we can try to get the first character to be something. And then if we want to get the first two characters to be something, we can still do that, but it'll take us slightly longer. So I wrote just to quickly demo this, because this part is very, very important. I wrote a little script today. It's called Find the Knots. It's written in Python. And basically the way this works is we want to find a hash that begins with a certain number of zeros. So let's say we want to find a hash that starts with 2 zeros. Put the number 2 there. And now I want to find the SHA-256 hash that we were just talking about. And I want to find the hash that, so we were just looking at hello world. I want to know what other combination of letters I can put here after hello world that'll give me 2 zeros at the beginning of the hash. So okay, so I'm just running this. Where are we? There. Okay, so searching for hash with an output that begins with 2 zeros should take about 256 tries. Each one of those characters represents 16 different possible letters. So if you just want to get a specific result for the first character, it will be 16. If you want to get a specific result for the first two characters, it's 16 times 16, which is 256. So we found the matching nonce. So nonce is just a random string, a random set of characters that will help us for this for one instance of whatever we're trying to do. So it took 474 tries. It took 0.002 seconds, and that was the nonce that resulted in the hash. It actually gave us 3 zeros. So we see this one starts 000CCD. So if we go back to our web page and we put that there, see 00CD. All right. So that took 0.002 seconds. So it just 250, just getting a set of the first two characters is pretty simple. Let's higher the stakes. Let's try getting four zeros. Again, it took 0.1 seconds, and it was. Oh, we got the word bike in there. That's pretty cool. Yeah, we got 4 zeros. Let's higher the stakes again. See, but notice it took a bit longer. It took 23,000 tries instead of 474 tries. It took 0.1 instead of 0.002. So let's raise this to 5. There you go. Now it's taking a bit longer. So it should take up to 1 million tries. There we go. And it took 1.1 million tries. It took 5 seconds. And this was the nonce that gives us that. That gives us 5 zeros at the beginning. Okay, so this is it's for a computer this is trivial, but it took 5 seconds. So somebody in the late 90s, somebody proposed that we use this as a system for stopping spam. And the way that would work is every time you send an email, you should take the entire text of the email. So we'd have so you take the whole email, put it through this SHA-256 hash, and give me the nonce, give me these characters that when added to the email, gives me 5 zeros at the beginning of the hash. So just do a tiny bit of effort, 5 seconds worth, to show me that you're legit. Because if you're a spammer and you're sending out 1 million emails an hour, you're not going to have 5 seconds per email. Okay? Is there any questions on that? Because that's important. Okay. Okay, so that's hashing. That's taking some words, putting it through a mathematical function, getting this long output, and we have this system where we can just, there's no way to predict it, but just try a bunch of combinations until we can get a bunch of zeros at the beginning. All right. Okay, so that's hashing. Next one is blockchain. Now that we know what hashing is, you take some information, you put it through a mathematical function, and then you come out with a hash. So what we can do is we can write some information, and that information is in the green. So let's say our information is January, and you can almost think of this as like an email. So think of this as this is January, and we hash the word January, and we come out. We hash the word January. We hash block 1. Previous hash is 0 because this is the first email or message, and then the hash of those 3 pieces of information will be this long number here. Okay, and now you can think. So now, if anyone has that long number, they can verify that whatever's in the actual email, whatever's in the actual message, is correct. Because if you change even one thing in that message, if you turn the Y into some other letter, or if you add a period, then that hash will change, and everyone who has that hash will know that you changed the message. Okay, so so now we have this message here, and we have the hash. This is a block, and this is what they call a block. Now I want to send another email, and when I send this email, I'm going to use this email to almost like secure the previous email. So I'm going to take this next email, and I'm just going to put the data will be February, the block will be 2, and the previous hash is going to be the hash of the previous block. So now you can almost think of it as like the signature of the previous block in this block, in this email.
That becomes part of
And that becomes part of the data.
That's your hash.
Yes. And now we hash all this information over here in the green, and we come out and we get the resultant hash of this hash over here. So now, if anyone who has this hash can now say, give me all the blocks in the blockchain. And in this case, there's only 2. Now, since this entire block and this hash relies on the fact that this block is in a certain state, looks a certain way, if anyone changes anything in this first block at any point, even though I only have by just having this hash of the second block, I'll know that. Because this hash relies on the fact that this block looks the way it does.
But you have to go back all the way to the beginning and check every hash.
Yes,
Make sure the first block has
that's correct. Yeah. And then it works. And then same thing when you get to the next block, the third block as well. You put in your information, you put in the block number, and then you put in the hash of the previous block. And again, you hash that block. All right, and the hash of that third block contains in it the hash of the second block. So each block is securing the block before it, and you can almost think of it as like a chain link. You know, when you have a chain and it's linked together, each link is holding onto the link before it. So this hash relies on the fact that this hash is correct. And this hash down here relies on the fact that this hash is correct. So as long as you have one of the hashes later on in the blockchain, you can then go back and verify, you can make sure that everything else in the past makes sense. And if anyone changes anything, so now imagine that this is now 1,000 blocks long. If anyone changed anything in any of these previous blocks, the block for the final block, or at some point, will be corrupted, and you'll know it right away.
You always have to start from the top, going out.
To verify, yeah.
But what's stopping somebody from corrupting someplace in the middle and then continuing down the chain?
And then spoofing that and sending that to everyone else. Very good, we'll get to that. Okay, so if you understand this, you understand blockchain. This is what blockchain is. It's basically taking a little bit of information, hashing it, and then taking some more information and hashing that with the hash of the previous block. That's it. That's blockchain.
What's the purpose of having block numbers then?
Just to know just for reference.
I mean, the
Techni-
hashes themselves comprise the reference.
I mean, technically, you can store that information someplace else, but you have to know.
Well, via the link of the hashes, you're going to know which one comes before.
Assuming it's a linked list and it points back to the. You can ask Jay about that. You can about linked lists. Yeah, assuming each block points to the previous block, then you don't need numbers, but not necessarily it doesn't need the number. The point is that you have information here and you hash it, and then you use this hash in the data of the next block. So each block is relying on the block before it. Cool? Okay. Okay, so a blockchain is a continuously growing list of records which are linked and secured using hashing. Each block is fundamentally linked, tied to the block before it like a chain. Okay, so we have one block here, block number 1. Very often it has the time that the block was created. You can put some data in that block. Let's go back. We can put some data in the block. Abe sent Bob $100. Okay, and then we hash this information, and then let's just say 87, just for convenience sake, is the hash of this block. Right, and this is a format of what we're hashing. Just we're taking 1, 0, the date, and then the message. All right, now we have a second block. We take the previous block, the date, two pieces of data. Bob sent Charlie $75, Bob sent Derek $10, and again we're hashing that. So this 31 depends on the fact that this number is 87. Right? If this block changes at all, then this hash won't be 87, and then this block will be invalid. Okay, so if I have this block and it points back to this block, but this block doesn't equals 87, I know someone messed around with the information, right? And works the same way. So the hash of this block is 31. We put that into the data of the next block. We hash this entire block, and that block is 63. So each block is relying on the block before it. All right, so let's say somebody did want to go in and change some information. All right, so, yep.
The format of these blocks are standard.
No.
So if you switch around the order.
In a given system, it's standard. Yeah. In a given, meaning this is a concept of blockchain where you have data and you hash it and you use that hash in the next block. Different blockchains can implement that in different ways. But for any given system, yeah, there has to be a consensus or agreement on exactly what the format of the block is. Yeah. Okay. So this is a blockchain that we had before, and it said here Bob sent Charlie $75, and now and the hash is 31, and we see that we.
Make sure I'm following your example.
Yeah,
here.
please.
With this example, you'd have to go all the way back to the beginning to understand what Bob's quote-unquote balance is. You'd have to trace it all
Yes.
the way back to blocks.
Yes, you'd have in order to verify.
You're not posting any totals here.
Exactly. Yeah. In order to, when you get a new transaction, in order to verify that person had the balance to send, you need to go back to the very first block. Yeah. Okay. So here's the blockchain that we were looking at before, 3 blocks. And over here it says Bob sent Charlie $75, and the hash is 31, and we use that in this block. Now let's say Bob goes and changes this to 50. Now it changes the entire block. Now the hash of this block is 89. That doesn't match. If we put 89 in here, it doesn't match this block at all. And therefore I know somebody messed around with something.
But it doesn't tell you who or what.
It doesn't tell you who or what.
How do you prevent people from concurrently trying to add in the same place?
Very good. Good question. We'll get to that. Okay, so this is the concept of blockchain. If you understand this, you understand blockchain. When you hear people talking about blockchain, you know what they're talking about. Okay? Boom. All right. Okay, so now, right, so Bob changed this 50. That invalidated this entire block, and so on and so forth. It invalidates all the blocks after that, so everyone who has this blockchain knows that something's off right away.
But there'd be no way to fix a mistake unless you just had another transaction that just manually corrects the mistake.
No, you invalidated all the blocks.
I'm saying, so if you realize that, 5 transactions ago there was a mistake, there would be no way to correct it. You just have to add a new transaction
Correct.
to the end of the blockchain
Yeah.
with some sort of
Yeah, there's no way to fix it. Yeah. Yep. Okay, so that's blockchain. If you understand that, you understand blockchain. Okay, so we went through hashing, and then we went through blockchain, and we saw how blockchain relies on hashing to secure each consecutive block.
So is there some security against somebody doing this maliciously?
Yeah, so we'll get to that.
any particular algorithm to hash, or that's chosen by the system.
So Bitcoin happens to use SHA-256. SHA-256, that's the hashing algorithm. Right? It's used by the NSA. It's used for top secret classified documents. It's as secure as they come. Okay, so hashing, blockchain. Next technology, the third or the fourth, is a distributed or peer-to-peer network. Okay, and basically the way this works is each of these clouds represents another computer, someone else's house, or another server. And we see here that everybody has a copy of the entire blockchain that we were just talking about before. And now, we can see here how every single computer is also connected to a few other computers. So now when anyone wants to add a new block to the blockchain, to add a few transactions, the way this works is that, let's say Abe wants to add a transaction, add a new block. So what he'll do is he'll send that information to the 3 computers that he's connected to. He'll send it to Bob, he'll send it to Charlie, he'll send it to Derek. Then Bob is connected to Mike and Evan, and Derek's connected to Evan and Mike. And we can see here that all the computers are interconnected. So as soon as one person sends out some information, within a few seconds, very, very quickly, everyone else has that information. Now, the cool thing about this is that there's no one's in charge. No one's coordinating. I mean, traditionally, when you had information that was distributed widely to a bunch of different computers, there was one computer that was centralized, one computer that was like the source of the information, and that one computer distributed it to all the other computers. In a peer-to-peer network, there's no one computer that's in charge. Everyone is in agreement with what the information looks like, and whenever somebody sends some information, they just share it with everyone else.
Somebody's in charge of where the network is. Like what nodes are.
Let's say I'm Abe, right? And I know Bob, and I know Charlie, and I know Derek. I connect my computer, I network my computer to their computers, and I send them information. That's all I'm doing. No one's in charge of that. I'm relying on my ISP.
There's a start where nodes that start off the network, and there's some way that you can find them. And let's say theoretically I had access to the source code of Bitcoin, right?
Right.
And I change the location of the network, I could technically take down the network.
No, because the network has nothing. The source code of Bitcoin has nothing to do with the network. I run the page. I don't want to talk to any of your IP addresses. I'll go find my own IP addresses to talk to, but it's completely up to you. Okay.
So let's say somebody puts out some malicious IP addresses somewhere, and
We'll talk about that. Yeah. Okay. Okay. So this is a peer-to-peer. Yeah.
Just a concept right here. I mean, obviously things are sort of working blazing fast, but isn't there a theoretical possibility that Charlie tries to send something to Mike only to find out that somebody's already taken that hash because Derek had already sent it to him?
Yes. Absolutely. Yeah.
It'll cost more than it's worth.
No. Yes. And we'll get to that. Yeah. All right. There are flaws. I mean, let's not call them flaws. This is a peer-to-peer network. It won't work off the cuff for every application, but this is the concept. Okay? When we apply it to Bitcoin and into cryptocurrency, then we'll work out all those kinks. Okay? But this is a concept of a peer-to-peer network where everyone is running the same code, everyone has the same information, and I can, on my own, connect to anyone else who's running the same code and share information with them. And they'll share my information with other people, and when they send me information, I'll share it with other people as well. And this way, nobody is in charge, and everyone is sharing the same information. Okay, so that's three. So we got hashing, we got blockchain, and we got a peer-to-peer network. Number 4 is digital signatures. Okay, and this is the last one. This is the last concept and technology that we have to understand in order to understand Bitcoin. So in real life, when you go to the bank or you have any paper that you want to indicate that you agree with what's written on this paper, you have your physical signature. You sign it with a pen. Now, there's the electronic equivalent of a signature on a paper is called a digital signature. And basically, and the way that works is with math. Is that you mathematically affirm or guarantee that you agree with with the contents of this information. And this is the way it works. So we have Alice and we have Bob. Those are typically the two characters that are used in this context. Okay, so Alice buys a car from Bob, and she's sending it an IOU, and she says, "Dear Bob, thanks for selling your car to me. I owe you $5,000. Alice." She sends that in an email or a text, and Bob says, "Yeah, I don't really trust you. Like that's not good enough. Like an email or a text is not good enough. I need to be able to prove that you actually sent this to me. I need you to sign it." So what Alice does is she creates. So in traditional cryptography, when you encrypt something, so you create one key, right? With crypto systems like there's AES and DES, some of the older crypto systems, you create one key, and that one key is used to encrypt your message, and that same exact key is used to decrypt your message. But in the late 70s, it came out with like RSA and other cryptographic systems where you can generate two keys. One key is used to encrypt, and a different key is used to decrypt. Okay? So what Alice does right? And so the encryption key can only be used to encrypt. It can't be used to go back, and the decryption key can only be used to decrypt. It can't be used to encrypt, where it goes one way. Alice goes and she creates her two keys. She creates what's called a public key and a secret key. She announces to the world, my public key is. She lets everyone know what her public key is. And then she takes the message and she encrypts it with her private key. When she encrypts it with her private key, anyone now can go and decrypt it with their public key. The only way to have a message that decrypts successfully with her public key is if you had her private key. All right? So any message that can be decrypted with Alice's public key must have been encrypted with her private key. So Alice has two pieces of information. She makes one public and one private. The private piece of information signs her message. So she takes her message, she signs it with her private key, and she puts that in the email. Now, when Bob gets that email, he says, okay, now I feel safe because I have this encrypted version of your message that only you could possibly have created. And therefore, if you ever try and deny that you owe me this $5,000, if you ever try saying that you didn't send this message, everybody knows what your public key is. And since this message is signed with your public key, it must have been that you signed it, that you encrypted it. What's that? That it was signed with the private key. Yeah, since it can be decrypted, since it can be read with the public key, it must have been generated with Alice's private key. Okay, and this is a mathematical way of signing anything. So you can take any piece of information and generate a public key and a private key, make the public key public, sign that information with your private key, and then everyone will know for sure that you were the one who made that message. Okay, and this is used all the time in the real world. You see it very often on Medium.com, where a lot of tech-oriented people publish articles. They'll put the hash, or they'll put their signed message, the signed article at the bottom of the article, so everyone can know that they actually did write that. And like when Edward Snowden was sending messages to news reporters, he gave them his public key and said, the way you know it's really me sending you those messages is because I'm the only one who can possibly encrypt messages so that they can be read with that public key that you have. Well, you can be right. So that's the thing. If I have a long message to tell you, it'll take me 5 minutes to read it to you. But if I want to give you my public key, so first of all, I can give you my public key over the phone in 30 seconds. Second, I can publish my public key. There are websites that are dedicated to hosting people's public keys. So if I want to go and look up somebody's public keys, there are websites that are dedicated to holding that information.
Why can I say I'm Donald Trump and my public key is put on that website and I write an article and everybody think I'm Donald Trump?
Because you don't have to write.
But who makes up the public? Who makes up with
I guess at some point you have to let everyone know that that's your key.
Authenticated source, either you tweeted it out with a verified, Twitter account of the individual, or you give a profile, something that people.
They worked it out.
I was like, but how do you know Edward Snowden? How do people know Edward Snowden's public key? Because he said, I am Edward Snowden.
Right.
This is my public key. But somebody.
Or he would say, I'm Edward Snowden, and check on this website. I put my public key there, and it's under that name.
But I can say I'm Edward Snowden and put on my public website.
It
as
has
well.
to be a first shot. I mean, you have to first. Nobody cared if he was Edward Snowden before he put out his first article. Once he put out his first article, the subsequent articles, how do you know it's still from the same guy? I don't think it's the first shot.
It definitely proved you're the same person who published the first one that was signed on that platform.
Okay. Whoever you expected it to come from, you take the signature and you put that together with a public key, and that should result in the original message that is actually there. Okay, and that's digital signatures. Or the hash. Okay, so it's hashing. Then we got blockchain, which is just a list of records that are linked. We have a decentralized or peer-to-peer network. That's a group of computers that share information. And then we have digital signatures, and that's a way to mathematically sign a message. And putting all these together, we can kind of imagine how Bitcoin works, kind of like we saw before, where A sends certain money to B, and then B sends certain money to C, and all that's in the blockchain. And if anyone messes around with it, then we'll know right away that it was messed around with. We might not know what, at this point at least, we don't know what the correct version is, but we'll know immediately that someone changed some information. Okay? So we have these four fundamental concepts, and the thing is that none of this is new. All of this has been around. Hashing and digital signatures have been around since the 60s. Hashing has been around since the 60s at least. Digital signatures has been around since the late 70s, I believe. And the first ones to introduce that were three Jewish guys, Ravesh, Shamir, and Edelman. That's the RSA. Blockchain was first discussed in the early 90s. So all this has been around. Even the concept of digital currency has been around for a while. There was something called eCash that was around in the 80s and 90s, and then something called B-money that was proposed by a guy named Wei Day in 1998. So again, all this has been around. So the question is, so what's the big deal? And the big deal is that, like everyone here was asking, how do you make this work? Right? How do we form a consensus? So if I have a blockchain, right, that works simply the way that we described earlier. Right. So if I have a blockchain, the way we described earlier, anyone can now go and start creating new blocks. We can have two different people creating blocks at the same time, conflicting with each other. Right? And then we have what's called a fork. So this block is based on this block, and this block is based on this block, and two people send them out at the same time. Let's say half the people receive this block and half the people receive this block. And now everyone is building on top of two different blocks. Now essentially what we have are two different chains. And this is what's called a fork in the chain. Also, even if you do maintain one, or I mean, and another problem, someone might actually maliciously do this, because what they might do is they might send money to one person in this block and then make sure they get whatever it is that they bought, and then quickly send the same exact money to someone else in this block. Right? And that would be called a double spend problem. So the problem here, and it's referred to as a Byzantine generals problem, is when you have a bunch of people communicating and there's no one central person maintaining order, and you have to assume that there are going to be malicious characters involved. People have an interest in changing or putting in bad information. How do you come to a consensus? How do you come to an agreement of which actual chain is the real chain? Which block is the real block? Okay, and that's where Satoshi's brilliance came in. Okay, because we had hashing, we had blockchain, we had digital signatures, we had all that stuff until 2009, but no one was able to make it work. And the brilliance, the piece that he came up with was called the proof of work. Okay, the proof of work, another phrase that people throw around, is what makes Bitcoin work, and what makes all the other earlier versions or attempts of a digital cryptocurrency not work. Okay, so what's proof of work? So before we get into proof of work, we have to understand a few more details of exactly how the Bitcoin protocol works. Okay, everyone following so far? Okay, so a Bitcoin transaction. What is a Bitcoin? When I send Bitcoin, what's happening? Okay, so I have a Bitcoin wallet. Okay, a Bitcoin wallet is simply, let's come here. This is one website where you can generate a Bitcoin wallet. So you come here and you just, it's going to generate a very random address. So it wants you to move the mouse around a lot to get like an external sort of randomness. You can see that number counting up. There you go. And it's going to create two keys. This is the two keys for what we just talked about with the digital signature. So there's the share key, the public key. This is a key that you tell everyone. And this is a secret key. This is what you use to sign messages with. And this is what people use to confirm that it was you who signed it. Okay, and this is a Bitcoin wallet. Again, when you hear people talking about Bitcoin wallets, this is it. It's basically a digital signature.
Special data that is beyond the regular pocket public keeper?
it happens to be with a very specific elliptic curve cryptography, but it's a digital signature that's used in plenty of other applications. Okay, so when I have so somebody sends me Bitcoin. The way that somebody sends me Bitcoin is somebody sends me Bitcoin. Let's start from there. Okay, so in the Bitcoin ecosystem, everyone knows that there was a transaction that was sent to me. Somebody sent me 2.5 Bitcoin. So again, we're going to use the same idea of a block that we did before, where we have some information and then we hash that information. So there was an input in transaction. So in a transaction, I have an input transaction, and that's some Bitcoin that somebody has sent me previously. Okay. Now I go and when that person sent it to me, they said that I'm the one who controls it. They said whoever has this public key is the one who controls this Bitcoin. So now I go and I sign this transaction that somebody sent to me. So now by me signing it, everyone in the system already knows that I'm the one who owns it because I have the public. Everyone already knows that whoever has the public key for this transaction can send it. So now when I sign it with my private key, everyone can confirm that the person who was holding the public key was the one who's sending this transaction. Okay? So I'm signing this transaction saying it's going out. So that's an input transaction. Now we have an output transaction. I'm going to send it to another address. Okay? And basically what I'm saying is whoever has the private key of this public key now controls this Bitcoin. Okay? So this is my public key. Somebody sent the Bitcoin to my public key. I'm now signing this previous transaction so everyone knows that I'm the one who received it. And now I'm also saying send that Bitcoin to another address. Okay? I'm saying send 2.4 Bitcoin to this other address and send 0.0998 Bitcoin back to my address. Essentially, if you see I bolded these two addresses, I'm sending it back to my address. Okay, and the idea here is that Bitcoin can be split up. Bitcoin can be split up into a 100 billionth of a Bitcoin. 100 billionth of a Bitcoin is one Satoshi. So Bitcoin can be split up, but a Bitcoin transaction can't be split up. Okay, so when I take this transaction, somebody sent me 2.5 Bitcoin. Now I can say, okay, take that transaction that came in for 2.5 Bitcoin, send 2.4 of it to this other person. So now whoever has a private key for this now controls this, and send the rest back to me because I can't send part of this transaction. I have to send the entire transaction. Okay? So I take all this information, right? And this just happens to be, so in total, the total input is 2.5 Bitcoin, the total output is 2.44998. And then I take all this information and I hash it, and this is a transaction. And this is what I send out to all other Bitcoin nodes around the world.
A little bit of leakage there. Where did that go?
Very good. So that's something called the fees. So I take the total input and the total output, and whatever's left over goes to whichever miner ends up putting this transaction into a block, and we'll get to that next. Yeah, but that's the way it works. There's always slightly less going out than going in, and the miner gets to keep that. Okay, so this is what a Bitcoin transaction looks like. Okay, so you could broadcast. You don't have to put in fees. You can output exactly the amount that you input, but then no miner will include that, and we'll get to that next. So the top one is a very simple transaction. There's only one transaction. So there's only one input, and there's two outputs. But you can, for the same price, you can have multiple inputs. So if 4 different people sent Bitcoin to my Bitcoin address, now all I have to do is take those 4 transactions, sign those 4 transactions, so everyone knows that I'm the one who's sending this. I have authority to release these funds. And now I'm going to send the Bitcoin, most of it to one address, some of it back, so 17HN, back to my 17HN address, and the remaining, so the total input is 11.2, total output is 11.195, and the remaining fees that aren't included are going to the miners. And again, I hash all this information here, and this is a transaction. This is a Bitcoin transaction. I take transactions that were sent to me, and I sign it, right? And I can sign it because whoever sent it to me said that I can sign it. So now everyone says, okay, cool, you're the one who got it, you signed it, you're releasing these funds, and then I'm sending it to someone else's public key, and now only that person can release those funds. Okay, so if you think about it, you never own Bitcoin. You own the rights to release the Bitcoin that were entered in a transaction. Right? Someone sent Bitcoin to this address, and now I have the rights to say, send this to someone else's address. Okay? That's a Bitcoin transaction. Bitcoin mining. Okay? So all these clouds represent different Bitcoin programs running on different people's computers. So whoever has this computer creates a transaction. They send it out to all the different Bitcoin nodes. Not necessarily does every Bitcoin node mine Bitcoin, and we'll see what that means in a sec. So Bitcoin transaction goes here. Then this computer sends a Bitcoin transaction to this guy, and this guy happens to be a miner. Okay, so the miner gets a new transaction that just entered the system. What does he do? So step one is he verifies the transaction. Number one is unspent. Make sure, yeah, it's great. First of all, he makes sure that it's signed, that you've signed this transaction, that you had permission to actually send this.
To verify that it's unspent, you got to go all the way back up to block 0.
You have created, it could have been created 5 years ago. It could have been created last month. You have to find when it was created, and then go back through every single block and make sure that this transaction was never used before.
An index to help you find that, or you just got to go through.
Some of the miners do keep an index, but it's not part of the core Bitcoin system. Step number one that the miner does is this transaction valid? If it's not valid, it throws it out, doesn't even look at it. The next step is it goes and it gathers several hundred transactions. It takes several hundred transactions and it puts together several pieces of information into a block of the blockchain. So first thing it does, it takes all those transactions and then hashes them together. Okay, so it takes like 1,000 transactions, puts them all together in a more complicated way, but essentially it puts them all together and gets a single number that is the hash of all those transactions. And that hash goes in a block. The next thing that goes in a block is the hash of the previous block. Because remember, a blockchain relies on the hash of the previous block. Another thing it puts in is the current time. And then, remember what we were talking about hash cache, and how when you send an email, you have to find some number, some random number, that when added to the email, it makes the hash have a certain number of zeros at the beginning. So you have to add an arbitrary number, and to make the hash of this entire block have a certain number of zeros at the beginning. And that's the idea of Bitcoin mining. So just to see here in more detail, so we have a block. So all this big green is one block. So there's two parts of the block. There's a block header and the block body. The block header is what we saw before. It's got the previous hash. So it's got the hash of the previous block in it. It's got the transaction hash. So you took all the transactions and hashed them. It's got that hash. It's got the time that the block was created. And it's got the nonce, or that number that when added to the block now results in a certain number of zeros as the output hash of the entire block. Okay? And then you hash this, just the header, and then you have to hash just the header, and the output of that is basically the previous hash for the next block. Okay? Also in a block is a block body, and the block body are all the transactions that are part of the block. Okay, so a Bitcoin block has all the transactions, but then what's hashed is just this information here, the previous hash, all the transactions are tied to this header because the header has the hash of all the transactions. Okay. And then one thing here is that you'll notice here that there's this transaction that has no input. Right? This transaction up here has an input transaction and has an output transaction, but there's this one block here that's got 12.5 Bitcoin that's got no input. Okay, and there's one of these in every single new block that's created, and this is called the Coinbase. So if anyone wants to know where the company Coinbase got the name from, it's from the actual Bitcoin protocol. So built into the protocol is that any miner who creates a Bitcoin gets to give themselves Bitcoin out of thin air. And the way that works is, in the beginning, it started off at 50 Bitcoin. Where every time you mined a block, you got 50 Bitcoin. And after, I believe it's 210,000 blocks, that got cut in half to 25 Bitcoin. And then after another 210,000 blocks, so at 420,000 blocks, the reward got cut down to 12.5. And that happens approximately once every 4 years. Another 210,000 blocks are created, and the reward again gets cut down in half. And this is the source of what people say, that there will ultimately only be 21 million Bitcoin ever created, and it's not. There's no number 21 million in the Bitcoin protocol. It's just if you do the math and work this out, it's the same way as constantly walking halfway towards the wall. Every 4 years, the reward gets cut in half. So there will never be more, just by definition of that, there will never be more than 21 million Bitcoin created. Okay, and this is how Bitcoin are created. This is where we have more Bitcoin get into the ecosystem. So that raises a problem. Okay, so in 100 years from now, there will be essentially no reward for mining a new block. So we can worry about that then, but hopefully by then the fees will pay the miners themselves. But that's a different discussion. But yeah, every block has this coin-based transaction that creates new Bitcoin and rewards the miner. Okay, so now that we understand that, so we understand transactions, we understand blocks. Question? So we have transactions, we have blocks. So what was Satoshi's? So how does that help us with all the problems we discussed before about people maliciously putting in fake transactions? Okay, so we have this existing blockchain over here. Okay, it's scaled down, and let's say in this block over here, where are we? Okay, so what are the things that miners do? They find the nonce to create the block, right? So that's not just to reiterate. It's not a long, complex math problem. This finding a new block. We showed before with this little script here. It's simply just trying it again and again and again. Okay. Number two, it's more like a lottery. It's just trial and error. The more computing power you dedicate to trying to find this one number that will make the entire block have a hash with a certain number of leading zeros, it's just a matter of trying harder. It's nothing complex. It's just doing it over and over and over again. And the key here is that there's no shortcuts. There's no way you can hack that. People say Bitcoin can be hacked. It can't be hacked. If you lose your private key, then people can steal your Bitcoin. People can create new transactions in your name. But the Bitcoin protocol, it's just about putting effort into it. And therefore, based on all this information, by this nature, blocks will be mined faster by a group than by an individual. Okay, so the more, if you have more people trying to create new blocks and just one person in their basement trying to create new blocks, just because the way the system works is whoever's putting in more effort will just find the next block faster. Therefore, the longest chain, by definition, the longest chain is the one with the most participants. Okay, so let's say we have someone here who put in a transaction over here and bought something from somebody, and the person sent them the product. Now they want to spend that money again. So what they're going to do is they're quickly going to go with their own Bitcoin node, and they're going to start working on a new block to try to invalidate this block. Okay, so first we have two blocks in this chain. Somebody sent out a transaction. That transaction was put into this block, and that block got dispersed, and all the nodes in the Bitcoin network got this block. So whoever was waiting for that money to come said, okay, cool, I'll send you whatever it is that you just paid for. Now the person who sent that transaction says, I want to spend that money again. So what I'm going to do is I'm going to quickly go and create another block, and another block, and another block, and that'll make this block that person relied on for getting their money invalid. Okay, and that basically someone says, I'm going to I spent money here, but I'm just going to create my own block, my own chain of blocks where I didn't spend my money, and therefore I can spend my money again. So they're going to start working on another block. But what we just said before was that everyone else is still working on this block, and it's only a matter of who puts in more effort, who's spending more time trying to find these blocks. So everyone else is working on this block, and if somebody has, and the way the system works is that it's configured to create a new block every 10 minutes. And the way that works is it's when I ran this script here, right? So it took me 5 seconds. It took me 5 seconds to find this hash. Now, if I had a much more powerful computer, it would have taken me 2 seconds. But the thing is, I was only looking for 5 zeros. So the way the Bitcoin protocol is set up is that pretty much every 2 weeks, it looks back at the average amount of time it took between each block. And if it took less than 10 minutes, it says, okay, everybody, add another 0 to the beginning of that hash that you have to find. And now it becomes that much more difficult for everyone to find new blocks. And if it saw that it took a lot more than 10 minutes for between blocks, then it'll say, okay, let's ease off the pressure, and you have to find a hash with one less 0.
So what if two people come up with the same answer at the same time?
So no one will ever, we have to remember, all the different nodes, all the different miners are getting the transactions separately. But so every single block.
When you say they're getting the transactions, so a transaction is getting sent to a specific miner, or they're picking it up off a bulletin board?
It's being broadcast. It's being spread out between all the different nodes that are connected. So meaning everyone is getting all the transactions, but not necessarily in the same order. And also, if I get 5,000 transactions and I want to create a block, I'm just going to pick out 1,000 transactions that I want to pick. So you can have 10,000 Bitcoin nodes, and every single one of them is working on creating the next block, but every single one of them is working on a different block, because every single one of them might have different transactions in it, some the same and some different.
How is it prevented that the same transaction doesn't end up with two different blocks?
Because if a transaction is in this block, and then someone else tries to send out a new block with that same transaction, no one else will accept it.
Only one block is accepted.
So let's follow this through. So this guy here, this malicious guy, is working on this block. Meanwhile, a new block was created. So now we're already 2 blocks ahead. By definition, because more people are working on this block is going to grow longer, faster.
So if I'm working on creating a new block that's got if I'm a miner, I'm working on creating a block that's got a specific transaction in it.
Yeah.
And somebody beats me to it, then I've got to go pick.
Yes. Then your work is essentially wasted. You pick up, you drop what you're doing, grab his new block, and now start working on that.
Okay, so you've got lots and lots of miners all trying to generate the next block with a different subset of all the available transactions.
Correct. Yeah.
And one of them, who's going to pick? How is it determined which one is the winner?
So
The first one who comes up with the right nonce.
as soon as you come up with the right nonce, you send your block out to everyone else in the network. Everyone
It's not possible for two people to do
everyone,
exactly the same.
whichever block you happen to get first, you check it. Make sure that none of those transactions in that block were spent before. Make sure it's a valid block, and then you drop what you were doing beforehand and start working on the next block. Now, if another block comes along, you say, "Sorry, I'm already working on this block." So you.
Also, with the distribution, right? I'm not broadcasting to everybody. I'm broadcasting to a distributed network.
Right.
So I distribute. We both come up within a few milliseconds the same thing. He distributes to 500 computers. I'm distributing to 500 computers.
Right.
Which one will
So
eventually get accepted by everybody?
if
and which one will get knocked out?
both of those blocks are on this level, meaning they're both working off the same parent block,
Right.
whichever one you get first, you work on.
So
You work on
I
that.
have a network. I have 500 computers.
Right. So now you have 500 computers working on one and 500 computers working on the other, right? One of those networks are going to find the next block first, and then they're going to send that out. Okay? Because we said that the way this system works is whichever chain has the most people working on it will be the longest. As soon as the people who are working on this block see that this block was broadcast, they say, "Oh shoot, there's more people working on this chain because this chain is longer. And therefore, I want to get on this chain because this is where the action's at.
You might find out a few blocks later that you've been wasting your time.
It won't be a few blocks later, it'll be a few seconds later.
And you might find out that the massive change is 3 or 4 generations ahead of you.
It'll
Probably not, but theoretically.
Yeah, theoretically speaking. But the way this proof of work works is that whichever chain is the longest, by definition, it means that that's where more people are working. And therefore, that's where you want to be. So if you're working on a shorter chain, no one else is working on that chain with you, and essentially you can mine a block, but the Bitcoin in that block won't be worth anything. And that's what Satoshi introduced. Everything else about blockchain, about distributed networks, about cryptography, hashing, digital signatures, that was all around. But no one was able to figure out how do you come to consensus when you have two chains. The idea of this of Hashcash was around a few years earlier, where you can just iteratively keep on checking different nonsense until you find the correct hash. Satoshi's genius was he put those two things together and said, no, we can use this as a system of consensus because whichever chain is longest, by applying the Hashcash to the blockchain, whichever chain is longest, by definition, it means more people are there. And therefore, everyone's going to want to get on that chain.
When you get, let's say you're working on a block and a new one comes your way, is there a code way to know that block's ahead of you, or maybe perhaps somebody who's a little bit behind you sending you a strange block?
It refers to the block before it. It has the hash of the block before it.
Not just that, are the blocks numbered, sequentially numbered?
I don't think in the block itself. I don't think it's sequentially numbered. No.
But then, once you're 2 blocks ahead, then you have no idea if you're the same chain or if you're a different chain.
If you're 2 blocks ahead, but that'll take 20 minutes, give or take. And then you wouldn't accept that. You'd be completely behind.
Just one source node.
Yeah, no one's. Yeah, you're connected to
Do you
many.
even know the next block that you're getting is after that one, or it's from a different?
It has to refer to the latest block that you have. If it doesn't refer to the latest block that you have, then you don't accept it.
I think once the miner that figures out the nonce broadcasted, it's obvious to everybody else. I'm not a tech guy, but right, it becomes obvious to everybody else on the network that you found the solution.
Yeah, as soon as you find the solution, everyone knows it. Within seconds, it's propagated. So the only time you run into this situation is if 2 people come up with a block within a second or 2 of each other. And in that case, yeah, then you'll have a bunch of different nodes working on 2 different blocks. But then as soon as that next block is created, now that one will be sent out to everyone else right away. Right? So you'll have half the nodes working on this one and half the nodes working on this one. But then as soon as this one is created, everyone who's working on this is going to drop it and quickly run here. And that's Bitcoin.
If you go to blockchain.info, you can actually see this log.
Yeah.
Transactions being broadcast in a second.
Yeah.
So where's this log stored? How many blocks is that?
Everyone who's running the Bitcoin protocol on their computer has this log on their computer.
So if I decide I want to start mining Bitcoin, where would I get the log from?
So you download the program from the Bitcoin GitHub, their code. You start running the program. It comes pre-configured. It comes with a couple IP addresses that you can initially connect to, or you can go on Reddit or some other forum on Bitcoin Talk and find IP addresses to connect to, and then you start downloading the blockchain. And that can take, at this point, it can take a few days.
You're downloading it from everyone else.
Yeah, basically you're saying, okay, who has block number 1? Who has block number 2? Who has block number 3? And we're up to like 500,000 or 600,000 already.
Every node will have a full copy of every block.
Yes.
Mining.
That's a bit more complicated. We can talk about that afterwards. Every mining node will have a full copy, yes. Every mining node will have a full copy.
So there's no way to go back and mess with the log.
No, you because
Mess with everyone's log.
yeah,
There's no way to do that.
no.
So that's a big file then.
It's huge. It's 25, 30 gig. Yeah, it's very big. Okay, so that's, if you understood everything until there, that's it. That's Bitcoin. So the first half of the talk was explaining the concept of digital currency. We had that one problem of consensus. How do you agree on which chain is the correct chain? That's what Satoshi Nakamoto introduced with the proof of work, and that's Bitcoin. So just to take it from the top, you create a transaction. Transaction has inputs. You sign the input. You specify the output. You generate the hash of this whole transaction. You send it out to all the nodes that you're connected to. Step one. The miner gets it. They include your transaction in the block, and they mush together all the transactions. They get the hash of that transaction, and they include that in the header. And as soon as they find the nonce that makes this entire header have a certain number of zeros, they broadcast that to the system, and they get to keep their fees and their rewards.
Does a miner know which transaction to take in, which transaction not taken? Does he know which transaction has already been included in a block?
Yes, because they have the entire copy of the blockchain, they'll know if a transaction has been spent or not.
They need to check that every time a transaction comes.
They do need to check that. I don't think there's an index built into the protocol, but I would assume that all the big miners maintain an index. Okay, cool. So that's it for the slides. Okay, and that's any questions on that? So just
It doesn't seem scalable.
It
Another
seems
10 years
massively
from
clever
now,
and
right?
massively inefficient.
how so?
Because I mean, the scale is not linear, right? As you have, it's exponential.
It's an n log
And if
n
you-
log n.
Some form of this.
You got a double log n in there in terms of computer science terms.
Okay.
Because you've got a growing blockchain you got to check, and you got a growing number of transactions you got to check, and you're fighting against the log n of additional digits and nonce every so often, and it just keeps getting harder and harder.
Right. Well, that's the point. So, like, I mean, it doesn't seem like it can scale past another, I don't know, throw something out there, another 5 years, when if you have to know the full chain, that'll be
So
ridiculously large.
the miners have to know the full chain.
Yeah.
There are ways for regular people to run Bitcoin nodes on their own computer where they only have a scaled down version of the chain. But yeah, the miners have to maintain the entire chain.
Well, idea with blocks, that way instead of having to know the entire transaction log, you can just have, technically, if you want to apply it in a real world, not the cryptographic, if you want to adopt this as your own transaction log of some sort, you wouldn't have to keep thousands of transactions. You'd have to, eventually whittle down to 2, 3, 4, 10 blocks.
Why?
With the validate one block, then you just validate 1,000 transactions. So it does kind of condense it.
Yeah, but you have to keep those transactions so that people can refer back to them.
Absolutely, but in terms of the real world day-to-day validation,
Now let me just
1,000 transactions every single day.
let me just show just 5 more minutes, and then we'll break and we'll schmooze. Okay, so there's blockchain.info is one website that maintains a lot of information about the Bitcoin blockchain. So where are we? Okay. So this is a list. This is a running list of new blocks that have been created. So block 510,014 was the last block that was created, and it was created at this time. And this was the. You can see here today, most blocks are generated either by massive companies in China or other places that are dedicated to mining Bitcoin, or pools, people who get together and work together to mine. And then, so this is the block, and then this is the hash of that block. As you can see here, it's a lot more than 3 or 4 zeros. It's a significant number of zeros, and therefore it takes a significant amount of computing power to find this hash for this block. So if we go and we open up this, so we can click on this. This is a clickable link. Let's look inside this block. So this block has a height. It's the height, what number block it is. So 510,000. This is the hash of this block. This is the hash of the previous block. And if I click on this link here, it'll take me to the previous block. We have the time that the block was distributed to the network. We have the difficulty. This is just a measure of how many zeros had to be leading the hash that was the output of this block. The number of transactions in this block, 310. Output total, there was 822 Bitcoin transacted in this block. This is the hash of all the transactions. And this is a nonce. So basically, whoever created this block started from the number 1 and added the number 1 to all this information in this block here and said, okay, what's the hash? Number 2, number 3, number 4. And finally, it came up to this number, and it found that. And this is a nonce that resulted in the hash with the leading zeros over there.
At what point does it become the authoritative, most recent block?
As soon as people accept it.
But theoretically speaking,
Yes, theoretically speaking. So this
it could be revoked at some point.
Yes.
You find out there's a group that's faster, that's ahead of you.
Yeah, so theoretically, I'm not sure how blockchain.info works, but let's say blockchain.info posts this block on their website the second that they get it. It could be, theoretically, it's possible that most other Bitcoin nodes on the network received a different block that was generated a second earlier. But we won't know that for another 10 minutes until the next block is generated. When the next block is generated, that'll tell us which one of these two blocks is the real block. Because as soon as that next block is generated, either on the block that everyone else was on or the block that blockchain.info was on, that tells us which one everyone else was working on. Yeah, so I guess theoretically this latest block could really not be the latest block. And that's why whenever you're using Bitcoin, people will say, we'll wait for like 3 or 6 transactions, 3 or 6 confirmations. It's meaning, okay, it's great that you sent me money in this latest block, but let's wait for another 2 or 3 or 6 blocks on top of that till I know for sure there's no way this block is going anywhere. And that's why people sometimes say you have to wait an hour for your Bitcoin transaction to go through. It went through within 10 minutes, but I want to be double, triple sure that it's staying there.
And in order to prevent the double spend,
Yes.
you send to 2 different people on 2
Yeah.
different chains.
Okay, so this is the header, all this information, and then
How many Bitcoins were in this? It was 300 transactions, and how many Bitcoins? Let's say
822.
322 Bitcoins.
That's 9.4 million.
There's no relationship between the cost of mining and the amount of Bitcoin that's being transacted.
No relation at all. Okay, so this is the header. This is all the information that's being hashed. And then over here are all the transactions. So you can see here, so first of all, we see here, this is that Coinbase transaction. There's no inputs, but this is going to, there's an output transaction, and we can see here it's 12.5 Bitcoin coming out, and that extra 0.09 is from the fees. And then these are all the other transactions that are coming in. So this is the input, and these are the output addresses. And you can actually go in and these are all clickable links. Just one interesting fact here. So this is whoever mined this block. This is their wallet address. So if we open this up and look in here, so they just got 12.5 Bitcoin now. This is their public key. Number of transactions, 18,000. How many Bitcoin do they have? 190,000 Bitcoin. What's that worth? I don't know. I don't want to think. But yeah, basically, and you can see here that so this is their wallet. This is their public address. All the transactions in here you can see, or most of them, this is a Coinbase transaction because there's no input. Another Coinbase transaction because there's no input. Someone must have sent them Bitcoin here for some reason, 12.3 Bitcoin. But again, you see here, this is another Coinbase transaction. So this is their wallet, and they've got a lot of Bitcoin.
Let's see, anyway, why is their wallet information public?
So that's another thing. That's a good question. Another thing with Bitcoin, people think it's anonymous. It's not anonymous, as you can see here, right? If I
Can we go to that website and see what public key this is?
what's that?
You can put into the
Yeah. So let me.
any transaction or any wallet address, and it'll give you.
So I sent myself from Coinbase a little bit of Bitcoin earlier today. So this is the public address of the wallet that I created with something like this. So let's go to that public address. Like $3. Yeah. So we can see here, this is a transaction. So this is Coinbase sent me from their public address, and this is my address. So I wonder how many other people Coinbase sent transactions to, send Bitcoin to. So we can open up their public wallet, and they just sent it to me. Okay, that one was boring. Sometimes you'll see they sent it to like 50 other people, and it was like a couple thousand Bitcoin altogether. But essentially what I was trying to show here is that this is not anonymous. When I send Bitcoin to someone, I can track that Bitcoin until infinity. Every time that when I send Bitcoin to someone, I can watch their public address, and I can see when they send Bitcoin to someone else, and then I can see when they send Bitcoin to someone else. There's no name. By default, there's no name to the address. But if I know, once you have like a foothold in, and you know the name on one address, you can oftentimes infer the other addresses. So people who think that they can avoid taxes with this type of thing. So if you buy Bitcoin on Coinbase and then you send it to your private address, IRS will get all that information from Coinbase. So now IRS knows your wallet. Now, if you go and send the Bitcoin to one person and then send the Bitcoin to another person, and then you buy a pizza in a local pizza shop with that Bitcoin, or you go and buy drugs with that Bitcoin, the IRS has or if you go and you send that Bitcoin to 1,000 different wallets and then put it all back into one wallet and think, okay, I dispersed my Bitcoin and now no one knows who it is. There are companies who all they do is track Bitcoin transactions, and the IRS, the FBI, the NSA, if there's any way that they can possibly get a foothold into this, or if you spend that Bitcoin on a website, right? So they'll see that at one point that this Bitcoin was sent to a wallet from your Coinbase account, and 50 transactions later, you again spent that money. So they'll know that all those transactions in between were really you just trying to disguise your Bitcoin. So Bitcoin is not anonymous. It's just
Only because they got the initial confirmation to attach your identity from Coinbase. That was the whole.
Right.
That was the whole thing.
As I said, as soon as they as long as they get any sort of foothold in the transaction history, they can track you. Obviously, if you go and buy it from a guy in the corner, and then sell it someplace where no one knows who you are, then possibly you're okay. All right, that's it. Any questions?